Have you ever noticed how a blast of cold air can feel like a sharp sting, while intense heat feels more like a deep, spreading burn? Why is it that cold often feels so much sharper, so much more pokey than heat? It's just a fascinating question that takes us deep into the world of our nervous system and how we perceive temperature. The secret lies in the specialized nerve endings in our skin called thermoreceptors. We have two main types, one for sensing cold and one for sensing warmth. Now, here's where it gets interesting. The nerve fibers that detect cold are different from those that detect heat. Cold-sensing fibers, known as A delta fibers, are thinly myelinated. Think of myelin as the insulation around an electrical wire. This thin layer of insulation allows signals to travel incredibly fast, almost like an express train to your brain. On the other hand, the nerve fibers that sense warmth, called C fibers, are unmyelinated. They don't have that insulation. This means the signals for warmth travel much slower, more like a local train making every stop. So, when you touch something cold, the sharp signal zips to your brain almost instantly, giving you that immediate, piercing sensation. The burning signal from heat takes a bit longer to register, resulting in a sensation that feels slower and more diffuse. But speed isn't the only factor. The density and location of these receptors also play a huge role. We have significantly more cold receptors in our skin than warm receptors in some areas, up to 10 times more. Plus, these cold receptors are located closer to the surface of the skin. This high density and shallow placement mean that even a small cold stimulus can activate a large number of receptors very quickly, creating a strong, focused, and sharp sensation. Warmth receptors are fewer and buried a bit deeper, which contributes to that slower, more spread out feeling of heat. Think about it like pixels on a screen. The cold sensation is like a high-resolution image with many tiny, sharp points of data. The warmth sensation is more like a lower-resolution image, where the data points are fewer and more spread out, creating a blurrier, more generalized feeling. There's another layer to this mystery, the pain connection. Both extreme cold and extreme heat can activate our pain receptors, which are called nociceptors. However, the way they do it is different. Intense cold causes the blood vessels in your skin to constrict rapidly. This sudden change can trigger pain receptors, leading to that biting, stinging feeling. It's a very direct and immediate response. Extreme heat, however, typically causes damage by literally burning your tissue. This process activates pain receptors in a way that leads to inflammation and that characteristic throbbing, burning ache. So, the sharpness of cold is partly due to the rapid-fire signals from dedicated cold fibers, and partly due to the specific way it triggers our pain pathways. Let's consider an experiment you can try at home, carefully, of course. Imagine dipping your finger into a bowl of ice water versus holding it near a hot stove. The ice water gives you an immediate, sharp shock. The heat from the stove feels more like a gradual, creeping warmth that intensifies into a burn. This simple comparison perfectly illustrates the difference in how our body processes these two sensations. This difference in perception is actually a brilliant evolutionary survival mechanism. A sudden drop in temperature can be an immediate threat, leading to things like frostbite or hypothermia. That sharp, immediate warning signal from cold receptors tells you to react now, pull your hand away. Find shelter, put on a coat. It's an urgent alarm system. While heat is also dangerous, the danger often builds more slowly, giving you a slightly longer window to react before serious injury occurs. The slower, deeper sensation of heat serves as a persistent warning to move away from the source. So the next time you step out on a frosty morning and feel that sharp bite in the air, you'll know exactly what's happening. It's not just in your head. It's a complex and lightning-fast communication between your skin, your nerves, and your brain. It's the high-speed A delta fibers, the dense network of shallow cold receptors, and the unique way cold interacts with your pain pathways, all working together to deliver a clear and urgent message. It's cold. It's just another amazing example of how intricately our bodies are designed to perceive and navigate the world around us. Thanks so much for watching and exploring this cool topic with me. If you found this interesting, be sure to hit that like button and subscribe for more deep dives into the science of our everyday lives. See you in the next video.